Good evening and welcome to Cook the Science. I'm Thomas Michaels. I'm a professor of soft and living matter physics here at ETH Zurich in the Department of Biology. And I'm also a member of the Bringing Materials to Life Consortium and the World Food Systems Center. It's really wonderful to see so many of you here tonight. Such a packed room for a really wonderful topic, I think. For the people that are new to Cook the Science, it's a public lecture series here at ETH Zurich that we are organizing in order to bring science closer to the public. And we do this by using something that we all love and like, which is cooking. And so cooking provides such a wonderful range of examples of scientific principles at work. And so by being inquisitive in the kitchen, we can actually learn a lot about science and about the scientific method and how we approach science. And so every evening we have a different kitchen science topic that we are trying to make sense from the point of view of the science, as well as from a practical cooking perspective. And so the topic tonight, it's the science of cocktails. And so to help us navigate this wonderful topic, tonight we have Sarah Madritsch. Welcome, Sarah. Sarah has worked for over 10 years in different hospitality venues in Zurich and also in Bangkok. She won the Barkeeper of the Year award in 2022. And currently she works as a creative consultant for beverage programs in hospitality businesses. So it's wonderful to have you here tonight.
Thank you so much. Yes, thank you so much, Thomas. And I would like to say also thank you to the team at Taste Lab, Sue and Remo, for inviting me. It's really great to see so many people here tonight. And I can't wait to share with you what Thomas and I have been working on together.
But before we actually dive into the science and the art of cocktails, we cannot start a lecture on cocktails without mentioning James Bond. And so I bet you've all seen James Bond say this.
The martini, shaken and stirred. Shaken but not stirred. Or the martini, shaken and stirred. Broken martini, shaken and stirred. I'm sorry, we don't serve alcohol.
We don't serve alcohol here too, so actually what you have there, it's a mocktail, and we will have a lot of mocktails tonight. But I wanted to bring this forward, of course, because martini is really a classic, but also because this phrase, shaken, not stirred, actually has quite some science behind it. And we will actually try to understand a little bit of this science tonight. And very much in short, the idea is that shaken cocktails tend to be more diluted and colder than stirred cocktails. And we will actually try to understand why this is the case. But first, Sarah, what is your take? Do you prefer shaken or stirred?
Yes, so basically the martini cocktail, it's a spirit-forward drink. And the Vesper Martini, as it's originally called, it was created by Ian Fleming for James Bond, for his movies 007 and James Bond. And originally, when you shake a cocktail, you normally would need rapid dilution, and you would use it for ingredients that have a lot of egg, dairy, and fresh ingredients like citrus juices. Now, when you stir a cocktail, you would normally use that for just spirit-forward kind of ingredients. And so stirring a drink, you would need really gentle and controlled dilution. So you would do stirring for example, Negroni, old-fashioned, and the martini. So Bond's preferred method, therefore, is technically incorrect.
Oh, no, this is too bad. So would you actually serve James Bond a cocktail if he would come to your bar?
Not a shaken one, yes.
But if it's stirred?
If it's stirred, I will do it for him, because it's James Bond, so, you know. Yes. So before we get into the history and science behind the cocktail, I would shortly like to introduce one of my favorite quotes by a food scientist, author, and bartender Dave Arnold. So Arnold says, "Think like a scientist and you'll make better drinks." So Arnold views different ingredients such as spirits, sugars, and water as ingredients or subjects that can be measured and tested. And without of us even thinking about it, chemistry and physics is hugely involved when we're creating a cocktail. So it's kind of a combination of art and science altogether. And by using the scientific method, therefore, we're able to create better drinks as a result because of the consistency. Now, I would like to talk a little bit also about the historical evolution of the cocktail, because I find it quite fascinating how much it has evolved over the past 100 of years. Starting with the early 1800s. So before ice was even common, it was considered to be just really for the wealthiest of people. And this all changed when Frederick Tudor started to import ice from New England to warmer climates all around the globe. And the introduction of ice completely changed the way cocktails were being made. So back then, cocktails were enjoyed at room temperature with a combination of spirits, sugar, water, and bitter. So you can imagine it's really boozy and not such a nice thing to enjoy. And so almost around the same time, the word cocktail was first discovered in a New York newspaper. And the term cocktail actually came to mean a mixed racehorse that had a funny-looking tail standing up, kind of like a rooster. So therefore, this term cocktail started to mean a mixed drink or an adulterated drink. Now, the late 1800s saw the golden age of cocktails. So Jerry Thomas, also known as the founding father of American mixology, wrote the first ever book written about classic cocktails. Thanks to him, drinks like the old-fashioned, Manhattan, as well as Martinez became popular all around the country in the United States at that time. Now, during the 1920s and 1933, the United States made it illegal to produce, consume, and sell alcohol during the Prohibition period. Now, this was quite unique because it gave people the idea to have to kind of like illegally distribute alcohol. And by doing so, they used bootlegging as a practice, which was basically when you would hide alcohol within your boots in order to distribute alcohol illegally. Another really important factor that came out of Prohibition was speakeasies, which I guess some of you have probably heard of before. Kind of. So speakeasies were hidden secret bars where if you would go, you would have to kind of whisper the password very quietly in order to get in. And this was really important because in those speakeasies, the bartenders, since the alcohol was in such poor quality, they had to really mask the taste. So at that time, it was the first time that bartenders started to use fresh ingredients to make their drinks. Now, in the early 2000s, Sasha Petraske, also being credited of being the person who invented modern cocktail culture, started to revive speakeasy culture again and giving the cocktail world a kind of like craft renaissance. So his philosophy was to use fresh ingredients, homemade ingredients, as well as clear ice. Which brings us to today, the modern mixology world. So thanks to innovators like Dave Arnold, now we have so much access to different scientific techniques to order to make really incredibly new and creative cocktails.
And so I guess it's time for a little bit of science. And we are actually going to go through 4 techniques, modern techniques, and kind of discover the science behind it. But if there is one unifying topic that is really important for cocktails, is to understand ice and water. Okay, these are really 2 essential components of any cocktail. And understanding the thermodynamics and the energetics of these compounds, it's really important. And I would actually like to start by saying that water is so familiar to us, I mean, we probably give it for granted, that we actually don't think how weird of a substance it is. And so let me give a few examples. For example, you all know that water freezes at 0 degrees at atmospheric pressure. But if you think about it, this temperature, 0 degrees, is surprisingly high for such a small molecule. So actually, for such a small molecule, you would expect freezing temperatures that are hundreds of degrees lower than water. And let me make a few examples. So if you take, for example, liquid nitrogen, N2, it actually freezes at minus 210 degrees. Or if you take another example, oxygen, or O2, it freezes also at around minus 220 degrees. Now, N2 and O2 are both molecules of a pretty much similar size as water. Actually, they're a little bit more heavy than the water molecule, yet they freeze at hundreds of degrees less than water does. Very weird if you think about it, right? Another interesting fact about water is that it expands as it freezes. And this is actually opposite to most other substances that we are actually used to. This, of course, is very important for biology because it means that ice floats on the surface of water. And so that allows life in water to exist also in winter. And so, of course, without this property of water, life would not be possible in the way we know it now. Another interesting fact about water is that it has a surprisingly high heat capacity. The heat capacity is the amount of heat that we have to add to a substance in order to increase its temperature. And this, of course, comes from the various properties of water, as we will see, and it's the reason why it always takes so long to bring a pot of water to boil. And even more energy is needed actually to change the state of water. So, for example, to melt an ice cube of ice into water, it actually takes a surprisingly high amount of energy. And this, of course, is very important for cocktails because it's the reason why ice chills our cocktails. And so let's try actually to make sense of some of this weird behavior of water. Now, almost all of these different weird behaviors of water are actually in large part due to a wonderful, unique property of water, which is the ability to make so-called hydrogen bonds. And let me explain. So you all know that the chemical formula for water is H2O. So it means that, yeah, if you want to clap, yes, please clap. There will be more formulas coming up, so be ready. So you see here, so that means every molecule has two atoms of hydrogen and one atom of oxygen. Now, what is more interesting is actually to look at the shape of this molecule. So what you can notice is that this molecule is actually not straight, but it's actually bent, okay? And what you see here, these sticks here are actually the bonds between the atoms. They are so-called covalent bonds. And what you can imagine here is that these bonds correspond to sharing of electrons. So that means that actually this hydrogen and this oxygen each share one electron. They put it in the common, and that's how they get bonded together. Now, even though the electrons in the bond here are shared between the hydrogen and the oxygen, it turns out that the oxygen tends to pull these electrons a little bit closer to itself. And so what it means is that actually there is a slight negative charge on the oxygen. And on the hydrogen, we have a slightly positive charge, which we denote with this delta plus and delta minus. And so this, of course, has importance on how water molecules interact with each other. Because as you know, opposite charges attract each other. And so if we have two water molecules, now what is going to happen is that the slightly negative charge on the oxygen here is going to attract the slightly positive charge on the hydrogen, and you're going to create a little bit of a bond between the two, which is what is called the hydrogen bond. And of course, this goes all the way. So this hydrogen here will form a bond with another oxygen on another molecule, and so on and so forth. And so this bond is, of course, weaker than the covalent bonds that you have within the molecule. It's about a tenth weaker, but actually it determines a lot of the properties of the collective properties of water. So if we are actually to understand a little bit how liquid water would look like, we would have molecules of water floating around. They jiggle around, they move past each other, they form some hydrogen bonds, but there is thermal agitation, and this thermal agitation moves the molecules around. The higher the temperature, the more jiggling motion they have, and so this makes sure that not all of the all these hydrogen bonds are stable. Now, in a solid structure, when we have ice, then these molecules order in a particular crystalline fashion, and so due to these hydrogen bonds. And the critical temperature at which this transition happens here is, of course, determined by the balance between the jiggling energy of the water molecules and the sticking energy of the hydrogen bonds on this side. And so this is crystallized in this formula here, where you see that at this critical point there is a balance between the internal energy U, which is the energy of sticking, and the molecular energy of agitation, the jiggling energy that depends on temperature. And of course, now we can start to understand a little bit why the freezing point of water is so high. And this is due to these hydrogen bonds here that contribute to the sticking energy. And so you see from this equation that if you have a high sticking energy here, that means that you need a higher temperature for this transition to happen. And we can visualize this transition very nicely with this wonderful simulation here, where you see water freezing. So you see on this side here, the ice, so the molecules ordered in this crystalline fashion, and the ice that is growing. And on this side here, we have the water molecules in the liquid state. So you see how they jiggle around due to thermal motion, and how they latch onto the crystal structure of the ice, and they start to order due to these hydrogen bonds. But of course, you see also how the molecules, even in the crystal structure, still move around. This is because the ice still has a little bit of temperature. So there is a little bit of jiggling motion still going on. Now, the hydrogen bonds also account for the surprisingly high heat capacity of water. And so the heat capacity is the energy needed to increase the temperature of a substance. So if we add heat to water, the temperature is going to increase, and this is because the energy that we are putting into the water is going to go into jiggling motion, so the molecules are going to move faster around. But exactly how this energy is going to then turn into motion depends on the substance, and this is what the heat capacity is trying to tell us. Now, the heat capacity is defined through this equation. So what you see here is you have Q, which is the energy that we have to input to change the temperature of, say, for example, water by an amount delta T. And so the energy that we have to spend to change the temperature of water by delta T depends on the mass of water that we have, M, and the heat capacity, C. And the heat capacity tells you how easy or hard it is actually to increase this temperature. Now, the heat capacity of water, it's this value here. So it's 1 calorie per gram per degree. So which means that in order to heat up 1 gram of water by 1 degree, you need 1 calorie of energy. So keep this value in mind. It will come back later. But where does this value come from? Well, again, it comes from these hydrogen bonds. And the idea that even in the liquid state, these molecules can transiently form these hydrogen bonds that constantly break and reform. And so when we are now adding energy to our system, of course, this is going to translate into motion of the particles. But because of these hydrogen bonds, it's a little bit harder to put these molecules into motion. And so that's why it actually takes a surprisingly amount of energy to heat up water. Now, interestingly, ice also has a heat capacity. Being a different form of water, though, it has a slightly different value. So it has different thermodynamic properties. And another interesting value that you could potentially remember, because it will become later in the lecture, is that the heat capacity of ice is about half the heat capacity of water. So it takes about 0.5 calories to heat up 1 gram by 1 degree. And so to warm 1 kilogram of ice by 1 degree, it takes 0.5 kilocalories of energy. So we have seen what happens if we now have, say, water or ice, and we put energy into the system, the temperature is going to increase. Now, what happens at a phase transition? So when the ice goes into water or vice versa. Now, something very interesting happens, which is summarized in this graph here, where you see on the x-axis is the heat added, and on the y-axis we have the temperature of water either in the solid state or in the liquid state. And so what you see, of course, is that if we are in the solid state or in the liquid state, as we had our heat, the temperature is going to increase. It's going to increase faster in the ice because of the smaller heat capacity. But what is interesting is that when we reach 0 degrees, which is the critical temperature, now you see that the line is flat. So this means that actually we keep adding heat to our system, but the temperature is not going to change. So it remains constant at 0 degrees until we have melted all the ice. And then it will start to increase again. And so how can we understand this? Well, the reason for this is that when ice melts and goes back into water, the molecules of the ice absorb energy from the surrounding. So heat energy is taken from the environment to melt the ice. And this energy is used to break the bonds between the water molecules here. And so that's why when you add energy, this energy is not used to turn into motion of the molecules, but rather it's used to break this bond. And so until you've broken all of these bonds, the temperature is not going to increase. And this, of course, is very important for cocktails because this is how ice chills your cocktail. By melting, it takes away energy from the environment, in particular from your drink. And so the drink is going to cool as the ice melts. Now, of course, the opposite is true for the freezing process. So the freezing process actually releases heat, which seems actually a little bit counterintuitive. But for example, you might have noticed that when it starts to snow, the air feels a little bit warmer, and this is because of the formation of the ice crystals. And so this behavior here is called latent heat. And so the latent heat is defined by this equation here. And it's actually, this equation tells you the energy that you need in order to melt your ice. And so when we approach a phase transition, the curve stays flat because now we need to input energy to change the state of the matter, break the bonds. And so the amount of energy Q that we need to use in order to melt a mass m of ice depends on the mass of ice times the latent heat of fusion L. Now, for water, the latent heat of fusion is 80 calories per gram, which means that if we have 1 kilogram of ice, it takes 80 kilocalories of energy to melt it completely. And this is actually a surprisingly high amount of energy. It actually corresponds to the energy stored in 60 AA batteries. So it's really a huge amount of energy. And maybe remember the value of the heat capacity of ice that I told you before, 0.5 calories per gram per degree, which means that in order to increase the temperature of 1 kilogram of ice by 1 degree, it takes 0.5 kilocalories. Compare it to the 80 kilocalories that you need to melt 1 kilogram of ice. This is actually 160 times larger. So what does it mean? It means that when we add ice to our cocktail, two things happen. The ice warms up, and then it starts to melt. But most of the energy that is taken away from the cocktail is used to melt the ice and not to warm up the cocktail. And so the consequence of this is what has been baptized as the fundamental law of cocktails. Actually, this is not my invention, I wish, but comes from this wonderful book, Liquid Intelligence. And the law tells you this: there is no chilling without dilution. And it's a really profound concept. It really tells you that chilling and dilution are connected. The ice chills your cocktail because the ice melts, and by melting, it takes away energy from your liquid. And by melting, it also dilutes the cocktail. So the two things are necessarily connected. More chilling means more dilution. And this is the reason why shaken cocktails are more diluted and colder than stirred ones, because the vigorous action of the shaking breaks the ice and makes actually the melting process faster. And so you melt more ice, which means you lower the temperature more, and at the same time you dilute more. Now, of course, in the book, this fundamental law of cocktails comes in a sentence with words, and so I couldn't resist to turn it into an equation. So that's my formulation of the fundamental law of cocktails, where you recover the equations that we've seen before. So we are actually using tools that we've learned just a few slides ago. So on this side here, you see the energy that I need in order to melt my ice, a mass m of ice. And on the other side, you see the energy that is taken away from the cocktail, which depends on the change of temperature. So m ice is the amount of ice that melts. So that corresponds to the amount of dilution. And on the other side, delta T drink is the change of temperature of the cocktail. That's actually the degree of chilling. And so you see, dilution equals chilling. Okay, so that's the fundamental law of cocktails. And we will actually see it in action later on. Now, another interesting consequence of this is that you need a lot of ice in your drink. Okay, so if you think that bartenders actually rip you off by giving you a lot of ice, it's not true. And I have actually used the equations that you saw before to calculate the final temperature of a cocktail. If I take a drink of like 100 grams, starting at a temperature of 20 degrees, and I add increasing amounts of ice at minus 18 degrees, so straight from the freezer. And what you see is that as I increase the amount of ice, the temperature of the cocktail goes down until you reach a critical point at which the temperature then stays constant at the equilibrium value. Now, of course, that means that if you have too little ice, all the ice is going to melt. You're not going to chill your cocktail very much. And also, the cocktail is going to warm up with time. And so you need to add at least this amount of ice in your system in order to keep the temperature, so have leftover ice that keeps the temperature constant, because now you have an equilibrium, the ice in equilibrium with the liquid, and so that's going to stay at the equilibrium temperature. Okay? Now, note how the equilibrium temperature is actually a bit lower than 0 degrees. Of course, it would be 0 degrees if it would be perfect water. But of course, the cocktail is not just water. It has sugars, it has alcohol sometimes. I mean, it depends if it's a cocktail or a mocktail. And of course, these lower the freezing point of water. So they act a little bit like the salt that we put on the streets in winter to avoid the formation of ice. So in the same way, the sugar and the alcohol, they lower the freezing point. So they do the freezing point depression. And so that's why the equilibrium temperature of the cocktail is going to be something more like -5, -7, and so on. And now I think this is enough of equations and science. I think it's time to do some experiments.
Yes, absolutely. So I thought, why not put it to the test, the shaken and stirred? And we're going to do that by using a dry martini as an example. And we're going to have 3 different kinds of martinis with all the same recipe, but the only difference being the technique that it's being prepared in. So we're going to do first a shaken martini, stirred, and then a freezer batched and pre-diluted. So basically, the freezer batched one has been already pre-diluted with water to equal to the same amount as if you would stir for 15 seconds. So we start with adding our ingredients to the shaker. So
you've already pre-prepared the mix.
I've already pre-batched everything. So that's just gin and dry vermouth. And now we add our ice, which is going to be 160 grams, which equates to roughly 3 cubes of ice.
And you see, you need a lot of ice.
Yes, yes.
As I said before.
It's like how fires have chef, bartenders have ice.
Yeah, that's why I'm useful in the bar, right? I can tell you this.
Perfect. So now we're just going to have to time our 15 seconds.
Yeah, so we need maybe a volunteer. Okay, so to time 15 seconds for us.
Yes, and I'll have Thomas here doing the honor of shaking this beautiful martini, since I can't do it.
So how do I do it? I just...
Yes, so basically what you want to do is kind of mimic the motion of a kind of oval shape.
Okay.
So you're introducing a bit of aeration and also shake it really hard as you can.
Okay,
yes.
15 seconds.
Like until your face turns red, yes.
Be careful there in the first row. So 1, 3, 2, 1, go. Gosh.
Now you can clap as well.
It's very cold.
Yes.
Stop.
Perfect.
Okay, I'm so bad at this.
So now you have to open.
So how do I do that?
So when you want to open a shaker, there is a kind of here a little opening where all you have to do is basically just click, and then you can easily open up your shaker.
That's cool. Very
nice. Perfect. So now we're going to strain our martinis into our little martini cupettes.
Do here. So this is for James Bond.
Yes.
Whoa, very fancy, very fancy.
And the freezer batched martini, it should come out of the freezer directly. But so we're going to pour the same amount as if it's been already diluted.
Wow, there is so much of the shaken one.
Yes.
That's more dilution, you see?
Perfect.
The theory works.
Yeah. So exactly. So I mean,
shall we check temperatures?
please.
So which one is going to be colder? So this one here, I don't know if you can see from the camera. How much is it? -4. Wonderful. -4.2, almost like my theory. Yeah, we're getting there. Perfect. And this one here, this is the stirred one.
Correct.
So this should be warmer. So you see it's less diluted. So we have much more liquid here than here. And it's actually 4.3. Okay, so it's actually 8 degrees warmer than the shaken cocktail. And this one is how much?
So you have to pretend now that it came straight out of the freezer.
Yes.
It should be around -10
It should
degrees.
be -10.
Exactly.
Well, we pretend it's -10.
So
Well, it's because it warmed up in the meantime.
yes, correct.
Okay.
Yes. I mean, visually, you can also see that the shaken martini, it's completely almost to the top of the wash line. It's completely cloudy. And by straining it, you actually added more pieces of ice inside. So it's going to continue to dilute.
Yes, I don't know if we can see, but there are all these like small ice shards on the
and
top.
with the stirred martini, you have a kind of like gradual, gentle dilution, but it's not going to be as cold as the shaken one. But therefore, you have a good viscosity, and it's like a nice texture. And the frozen one will have the best viscosity. It's going to be completely thick because it's more or less frozen. So in my opinion, you should always freeze, batch, and pre-dilute your dry martinis.
Okay, I think we should try it.
Please.
And I want to try this. The
It's
shaken
also
one.
very difficult to drink afterwards.
It's like water, this one.
Yeah.
Oh, no.
Yeah.
Well, so you see, it works.
Exactly. So,
Oh, yes, sorry. I actually put this one extra for you.
yes.
So this is actually to tell you, so she was talking about the higher viscosity. Of course, here this is just for pure water, but the idea is that actually the viscosity of water changes with temperature. And so a colder water means higher viscosity. And so that's why I personally like really cold water. And I think I like it because of the higher viscosity. And so it gives you a much nicer kind of feel. Of course, you have to change its temperature here because of the alcohol and so the kind of freezing point would be lower, but this is a little bit the idea. Okay, now it's time for some more interesting facts about bartending.
Correct. So, I mean, now we had a look at the science, and we talked a little bit also about melting dilution, and also as shaking and stirring. But now I want to take a step back and look at bartending kind of as a whole. And for me, the most important foundational building blocks are the knowledge of ingredients, your tools and technique, your sensory design, and of course, ice.
As we have seen.
Yes. So cocktails are not just a random combination of different ingredients. They're built on the knowledge of your cocktail classics. So the cocktail classics are basically the foundation or DNA of all the kind of drinks that you want to create. And working with spirits or non-alcoholic products, so it's important for you to understand where your spirits come from, how they're produced, and how they're going to affect your drink afterwards. And if you work with non-alcoholic products, it's also really important to kind of know how to replicate these flavors and textures that alcohol would give to your drink. Then understanding which kind of structure agents you want to use. There are so many different kind of acids, syrups, as well as sodas, which can add structure to your cocktail. Flavorings and garnishes. So if you want to use garnishes as a finishing touch to give more aroma to your drink, or if you want to use tinctures to add a bit more complexity or deepness to your cocktail. Then understanding how to work with different ingredients, paying attention to seasonality, and of course also paying attention to sustainability at every step of the way. And the magic all happens when you find a way to kind of balance all of these factors together. So for the bartender, there's a million of different tools that you can use, which you can also see right here. But I would highly recommend just the following for just if you want to make cocktails in your home. And with these tools, you can essentially make almost every single classic cocktail that exists.
So that's for Christmas, the wish list. So
Yes.
you can take note.
Yes. So starting with the measurement jiggers, and these are for measuring basically by volume all your ingredients. Then we have different kinds of cocktail shakers. The one that you see in front of you is a Boston shaker, but they have also different kinds of materials that you can use. Then bar spoons for stirring cocktails as such. And of course, strainers and fine strainers for straining out your drinks. Citrus juicers for pressing lemons, limes, oranges, and whatnot. And then, of course, the ice molds. And for me personally, I like to use these kind of mid-small ice molds, which are roughly 2.5 centimeters by 2.5, because they fit perfectly in your freezer. And you can use them actually for shaking, stirring, and also serving your drinks on ice. Now, before we were talking about shaking and stirring, but there's also some other techniques that exist in the bartending world. And this is building your drink. So if you would make, for example, the gin tonic, blending, if you make frozen cocktails such as pina colada, and throwing, so not throwing on the floor, but throwing between two vessels as the shaker, like this. And you want to do this because you want to introduce a lot of aeration to your drink. So you would do that for drinks such as the Bloody Mary, for example. And last but not least, a lesser known technique called swizzling, which is with a special kind of wooden stick, which has almost like roots. And this is used for drinks that use crushed ice and have a lot of alcohol and sugar inside them. So now we arrive to my favorite part of the cocktail creation process, and that's the sensory design. So the sensory design, of course, starts with an inspiration. And the inspiration is extremely important because it is the starting point for storytelling for your guests. And they can come from anywhere. They can come from food, different ingredients, or even emotions or colors. It's really up to you where you find your inspiration from. Then the cocktail DNA and trends. So by cocktail DNA, I'm basically referring to classic cocktails. So you're thinking about what kind of style of drink that you want to make. For example, an old-fashioned or a long drink or a sweet and sour daiquiri style drink. And of course, knowing what kind of trends currently exist on the market. So at the moment, it's very popular to make drinks that are either non-alcoholic or low alcoholic. So I think it's also very important to kind of pay attention to what currently exists. Then the taste. Finding the balance between all the different tastes, so sweet, sour, salty, bitter, kind of playing with them a little bit and trying to find the harmony together of them. Then textures. If you want to introduce different kinds of textures to your cocktail, or if you want to carbonate them, for example, if you want to work with espumas, or if you want to milk wash, which we'll talk about later. And in the end comes the glassware. So we decide which type of glassware, depending on what kind of function it will perform for the drink. And now we come to the topic of ice. So there's a lot of different kinds of shapes and sizes and clear and cloudy ice that exists in the bar world. And the most common one is the standard kind of ice, which you can see. Yes, you know which one I mean. So it's the standard kind of ice. And yes, this is the most common one for shaking and stirring and also for making drinks with. Then you have the large kind of ice blocks, which I personally really love, which you can see like over here. And most of the time, they're also clear ice cubes, and those are really useful for when you have kind of spirit-forward drinks like a Negroni or old-fashioned, which you want to enjoy at a slower pace because of the surface area that it's melting.
Yes, so the rate of melting depends on the surface. And so the smaller the surface, the slower the rate of melting is going to be.
Exactly. And the sphere basically does the same function as a large ice block, but it's round, so it has even less.
Yeah, actually, the sphere is the shape, 3D shape that has the smallest surface to volume ratio. And
exactly. And these are also quite, they're made famous in Japan because the Japanese bartenders, they're well known for kind of carving them by hand. And it's not so easy. I've tried. And also, these ones, you can also serve spirits with them because they melt at the slowest. Then we have crushed ice. And this type of ice is really useful for drinks that have a lot of alcohol, a lot of sugar and fresh ingredients because you need that dilution to kind of water it down. Then we have the Collins, which essentially looks like this, it does the same function for slow melting and dilution, just it's been fitted for the kind of shape of the glass. And now Thomas will talk a little bit more about the science behind clear and cloudy.
Yes, I mean, if you look at these cubes here, I mean, they look wonderful. I mean, you see, it's super clear. I've never made an ice cube like this. The cubes that make at home are like this, super cloudy, which of course is nice. I mean, you can observe all the trapped bubbles in there, and it's like, it's wonderful. But now I got a little bit obsessed about it, and I wanted to understand how can you actually make clear ice. And so one very interesting thing I've actually notice, of course, you kind of observe, but then you don't think about it, is that actually, if you look, for example, at lakes, frozen lakes, the ice that forms on lakes, it's actually clear. And there is actually a reason for this. It's because of insulation and therefore so-called directed freezing. So what you need in order to get your clear ice is this directed freezing. The reason why it doesn't work with like typical molds, like the silicone ones that we've seen before, it's because the ice freezes not in a directional manner, but it freezes from all sides. So if we were actually to do regular freezing, it would look something like this. So we would have our water, and now it would actually freeze from all the different sides. So the ice is gonna start from the outside and then go into the inside. But now, of course, in the water, we have dissolved gases, and we also have impurities. And so now all of these bubbles are not gonna escape. And so they get trapped in your ice. And so you get at the end a cloudy ice with trapped air and impurities. And so how can we actually make clear ice? Well, we can actually take inspiration from the lake. And as I said, we want to achieve this directional freezing. And so the lake is such a huge mass of water that it's actually insulated. And so because of the insulation, it really freezes only from the top in a directional manner. And so how can we do this at home? Well, we can do this by using an insulated container. So something like this one that you can actually buy, and I'm going to get one for Christmas. That you see, it's insulated on the sides. And this is very important because having the insulation, so if you do this in an insulated box, because the sides are insulated, the ice is going to freeze only from the top. And so you get this directional freezing. Now the impurities and the trapped gases don't fit in the lattice structure, so they're going to be expelled. And of course, this ice now takes a bit longer to freeze. And so if you time it right, that it doesn't freeze completely, you're going to be left with clear ice and all the impurities left down at the bottom. And so this is actually how you can make these wonderful cubes. And I'm really eager to try them out. Okay, so now it's time to explore some modern mixology techniques.
Exactly, yeah. So basically, modern mixology techniques is the combination of science with creativity to create new and exciting flavors for your cocktail. And today we'll be looking at 4 of my personal favorite techniques, which is cryo-extraction, forced carbonation, milk washing, and espumas.
Wonderful. So let's start with cryo-extraction.
Exactly. So cryo-extraction is basically the process of using freezing under pressure to force flavors into your cocktail. And Thomas, you will explain a little bit more about the...
So it's a very interesting technique. I actually didn't know it. It sounds extremely fancy, of course, because of the word cryo. And the idea is that it's very similar to how you make a syrup, right? So you want to extract the flavors, but now the typical way to make a syrup is to heat your mixture up. So, sorry, don't go too fast. Is to heat up your mixture. And of course, here you do the same, but actually by freezing. So it's actually quite interesting. And so, as Sarah said, this actually uses a property of ice, which we've seen before, which is the pressure of freezing ice. So the fact that the ice expands, so the water expands as it freezes, and this pressure can be used to extract flavors. And of course, because we are freezing, we can keep the flavors much better. So if you're using, for example, like mint or strawberries or so that are quite delicate, you can preserve the flavors and still extract the maximum out of them. And so the way it works is that it uses the fact that water expands as it becomes ice, so crystallizes less dense than water. And so why is this? This, of course, again, has to do with these hydrogen bonds that we've seen before. And it actually turns out that these hydrogen bonds here have an equilibrium distance. So there is a kind of preferred distance at which the molecules pack or put at a distance from each other, and this is about 0.28 nanometers. And now, in the ice state, the molecules pack each other in an ordered structure to make sure that all these bonds have the same length. And so this results in this organization that is a little bit of an hexagonal structure, where you see all the molecules are at the same distance, and there are a lot of hollow spaces as well. Now, in the liquid water, the molecules don't have to, they can slide around each other, they can move on top of each other, and so they don't have to keep that same constant distance. And so they form these transient bonds, but actually that means that the distance, the average distance between the molecule is actually smaller. And so we have actually a smaller density, a higher density, and therefore actually a smaller volume. And so this is why ice, when it forms, it actually expands compared to water. And of course, this is used to extract the flavors, because this pressure that comes from the expanding ice can actually break cell walls and so release all the flavors that we want. And of course, when you're freezing fruits and vegetables, this is exactly what you want to avoid. That's why it's not easy to freeze strawberries, and so they lose their structure. But in this case, we take advantage of this to extract our flavors. And so let's actually try one recipe with cryo-extraction.
Yes, perfect. Yes, so we're going to be having a look at strawberry cordial. And a cordial is essentially anything that has sugar, acids, liquid, and a flavor. So you have here the recipe, and I'll be demonstrating as well what I've done for you today. So we have already here 500 grams of strawberries, which have been pre-cut, and all the ingredients have already been added to. And this has already been in the freezer for 24 hours, and I've taken it out this afternoon to let it a bit thaw. And what you can see now is that it's really kind of deeply red, and the strawberries really release kind of all of the flavors inside. And if you would be a bit closer, then you could also smell that it still has this complete freshness.
It smells very good.
Yes, exactly. Yes, it does. So now what we're going to do with this is we're going to create a lemonade by having the cordial as a base.
So you take this and then you strain it.
Exactly. So the end result of this one is just to put it through a kind of cheesecloth and then just strain it out. And
do you mix it before, or you just leave it?
You don't mix it. So you just strain it out. And the cool thing is, with the leftover strawberries, you can dehydrate them, and then you have a snack. So that's also a part of sustainability as well.
You can use them as decoration.
Or you can use them as a garnish, up to you. Yes. So
see, I'm learning.
So what you're left with is essentially a really deep red strawberry color cordial.
It's wonderful.
Yes. So now we're going to build the drink. We have our glassware and our ice. So everything starts to stick together now. So, by the way, if your ice ever sticks together, you can use one of those to kind of just hack them. It's called the ice pick.
So add it to the list.
Yes. Yes. And now, very easy, we just measure out 50 milliliters to our glass. And the last step is to just top it up with some soda water. I mean, for the strawberry cordial, you don't have to make a lemonade. If you want to make something alcoholic, you can make, for example, a rum daiquiri with strawberry, or a gimlet, for example, as well. Then we just top it up with a bit of soda water. Give it a quick stir. And it's ready to be served.
Oh, thank you.
Cheers.
Cheers. It's wonderful. So I think you can take over the lecture and enjoy this wonderful drink.
Great.
So we have now our next technique.
Yes, so now we're going to get into the topic of forced carbonation, which is basically dissolving CO2 in a liquid. And this is really cool, for example, if you want to have homemade sodas. But there are certain rules when you want to carbonate ingredients. And the most important factor is that the liquid has to be cold, because CO2 dissolves better in a cold liquid. And we don't want to have any solid particles, so no cloudy substances within the liquid. And as well as filling the vessel only 75% of the way, because we want to allow some CO2 to come inside to dissolve into the liquid. And finally, once you've carbonated it, make sure that you open gently and slowly. Otherwise, you're going to create a little bump in your kitchen. Sorry.
No, because there was actually something to clap for.
Oh, sorry.
So let's actually, you made a few interesting points. So first of all, temperature. So you want a colder drink, not a warmer one. And also you don't want to have particles left over in your drink. So you want a clear drink. So why is this? So let's actually try to make sense of it. So first of all, we want to think about the solubility of CO2 in water. So this is actually interesting because we are perhaps used to the fact that certain solids dissolve in water, for example, sugar or salt. But perhaps you don't think about that also gases can be dissolved in water. And this, of course, again, for biology is very interesting because it's the way, for example, fish get their oxygen. So we get their oxygen from the air, but fish take their oxygen from the dissolved oxygen in the water. And so in a similar way, CO2, carbon dioxide, can dissolve in water. And how much we can actually dissolve in water is what we call solubility. So the solubility is the number of grams of gas that we can dissolve in 1 kilogram of water. And what you see here in the graph is actually the solubility of CO2 with temperature. And so this is actually very interesting because if you think again about the example of sugar, typically you're used to the idea that as we increase the temperature, the solubility goes up. So that's how we make syrup. We heat it up because at higher temperature, we can dissolve more sugar. But this behavior is opposite for most gases. And so in this case, for CO2, the solubility actually goes up as we decrease temperature. And so why is this? Well, actually, this can be accounted from the principle of Le Chatelier, which is something that you would learn in a chemistry class, which tells you that if you have a chemical reaction of a general form like A reacting with B to form the products C and D, then what happens is that at equilibrium, there is a relationship between the concentrations of the products, the concentrations of your reactants, which is the products of these concentrations and then divided by the product of the reactants is equal to an equilibrium constant. And now this equilibrium constant depends on temperature, depends on a range of properties. And so it depends really what reaction you have. And so when we're thinking about dissolving CO2 in water, we actually have a chemical reaction that can be very simplistically written down this way. So actually you form carbonic acid, which is why carbonated drinks taste a little bit acidic. And what is interesting is that this reaction is exothermic, actually, so it releases energy. And so this actually results in a particular dependence of this equilibrium constant with temperature, which means that as we decrease the temperature, the reaction is favored in the forward direction. And so we actually can dissolve more CO2 at lower temperature. Now, the other point that you made was about the clarity of your drink. So when you carbonate your drink, you want the drink to be pure and crystalline clear. And so the reason for this has to do with nucleation. And so nucleation is the way the bubbles form. And so I have this picture here because I just love it. It's a wonderful picture. So here what you see is the motion of the bubbles of CO2 in a champagne glass from laser tomography. And you see really some wonderful fluid dynamics going on. We won't touch it this time, but perhaps for another lecture it will be a very interesting topic. What you see, of course, is that the bubbles start forming from the bottom and then they go up, they become bigger, so they grow. But how do these bubbles form in first instance? So as I said, they form through nucleation. So nucleation is the idea that the formation of these bubbles, it's not very easy. And actually you need a critical size of the bubble for it to be stable. And so this is summarized in this equation here. So RC is the critical size or radius of the CO2 bubbles, which actually depends on pressure, depends on the supersaturation, which is the amount of CO2, and so on, and then the surface tension of your liquid. And actually what it turns out is that this radius is about 0.25 micrometers. And the idea is that bubbles that are smaller than this size are unstable, so they will actually shrink. And so you need to be above this size for the bubbles to be stable and able to grow. Okay? And so that's why it's actually not that easy to form these bubbles in first instance. And that's the reason why the formation of bubbles always needs nucleation sites. And nucleation sites are impurities, typically. Actually, anything that you have in your liquid where these bubbles can latch on. A little bit of problems in your glass, some kind of dust particle, or, for example, some leftover particles from, your juice or so. And so all of these nucleation sites are gonna help the formation of the CO2 bubbles because they help these bubbles to remain stable for a longer time effectively before they dissolve, and therefore they have a higher chances of growing past this critical size. And so that's why it's very important to have your liquid clear when you carbonate. Otherwise, you get a very foamy result in the end, right?
Exactly, yes.
So I think it's time to do a recipe with carbonated
absolutely.
drink.
Yes.
So what have you got for us?
I've prepared for you one of my cocktail creations using inspiration from a caprese salad, since I love that so much. And basically, it's the only homemade ingredient here is the basil soda, which you can easily make at home with simple tools. And I've already pre-batched every single ingredient here in this bottle over here. So what I'm going to do now is just to kind of demonstrate how we force carbonate.
Okay, so I need
But I need you, actually.
Oh, no, really?
Just to hold the bottle. Don't be scared.
Okay, sure.
So I've already carbonated once. So normally when we do forced carbonating cocktails, it's important to carbonate minimum 2 times so that we really have that level of CO2 that we want. So it's not been carbonated that much. You didn't hear any noise. So we want to kind of take out all the excess oxygen and just close it at the top. And then we just cap it. By the way, this is a kind of homemade tool that I created. I would probably recommend
that doesn't make it less scary.
But I would recommend you probably just to work with a soda stream.
Let's do it this way. So
yes. So now I have also the CO2 regulator where I can see how much PSI is going in. So now I carbonate. So you can see the bubbles are going in. And then I turn it off again. And then I just slowly release. And that's it.
Okay, that was easy.
Yes. So we'll just put that to the side. And now all we have to do is essentially just build the drink. So we'll add a few blocks of ice again. So now we're going to slowly open, and it helps to open it a bit sideways, then it's not jumping out straight away. So now that was a good carbonation. Good. So now we just pour it over into the glass and garnish it with a beautiful cherry tomato. Try to get it on top somehow. So, well, when you're, yes. Well, okay, not today.
Oh, thank you. Where is the mozzarella?
Yeah, that's for something to snack on the side. Yeah.
That's wonderful.
It's good.
Yeah, very nice. Thank you.
Very good.
Okay, so now time for our third technique.
Yes. So now one of my top favorite techniques, and I think you also said you were.
Yeah, now it's become my favorite.
Yes?
I had no idea about this technique.
Yes.
And it sounds a bit weird, but it's really good.
Yes. So milk washing. So it's basically using milk to clarify your cocktails. And the result is then a completely clear drink that is stabilized because it gets preserved. And yeah, Thomas will explain all the science that goes behind.
Wonderful. So actually, this is the time for your tasting. So you have on your table 2 drinks. One has been milk washed and the other one has not been milk washed.
Exactly.
And so this is actually, we're going to see the recipe later, but this is a tea
yes,
mocktail.
it's made from milky oolong tea because I wanted to replicate this kind of tannin and astringency that you would normally get in spirits. So in this case, I use tea to kind of replicate that. And on your left side, you should have the milk punch, the one that's a bit more clear. On the right is the unwashed one.
Yes.
Exactly.
And so the idea is you should taste it and taste the difference.
Yes, so start definitely with the milk washed one first. Yes.
And hopefully you should see that the non-milk washed one is much more astringent. It has this more pungent taste of tea.
Yes.
And this has been removed with the milk washing.
Exactly.
Which is like when you wash your clothes and you can remove the dirt. So with milk washing, you use milk that you add to your cocktail or mocktail, and then you deliberately make the milk curdle, like cheese, and then you remove the curds, and the curds take away with them the astringent flavors of the tea. And so at the end, you get this more balanced cocktail. And so that is exactly what I found very fascinating, but indeed it works.
Yes.
And I was so fascinated about it that I decided to, this is, more my level, to milk wash Coke. So I took Coke and I added milk to it. And then, of course, you get something totally disgusting. And I'm going to show you here. So this is the result. This is my attempt at milk washing. Then you can tell me how it is. So, of course, as we will see, you need an acid. And so what the acid does, it makes the milk curd. And the curds then are filtered. And what you can appreciate is that you see the curds actually have a very strong color. They are actually colored like the Coke itself. But if you look at the liquid that remains, it's actually clear. It should be clear. I didn't do a good job. And if I smell it, it actually smells of Coke. Do you want to try?
I will try. You tried already all my drinks, so.
I'm going to try the curds. So how is it?
It's not that bad, actually.
Yeah, no, it's like Coke,
it tastes
isn't
like
it?
Coca-Cola, but just...
And the curds, actually, they taste of nothing. It's like, they are just colored, but they don't have any taste. So what you see here is that the idea of milk washing is that you are removing, by creating these curds, you are removing some compounds from your Coke. And so in this case, it's the colored compounds that are staying in the curds, and the other flavors are remaining in the cleared, in the clarified liquid. And so in the same way with the tea, you have these astringent flavors that are binding to the curds and are taken away, and you're left with a clarified, more balanced drink. And so let's actually try to understand a little bit how this milk washing works. And so the idea is, as I said, that you add milk to a cocktail. And so milk actually contains, of course, a lot of water. It contains sugar in the form of lactose. It contains fat. Most importantly, it contains proteins, about 3.3% of proteins, vitamins, and minerals. Now, there are 2 main types of milk proteins, casein and whey. So if you're into cheese, you probably know these 2 types of proteins. And in particular, I'm very interested about casein. So casein comes in the form of micelles, which are kind of globular aggregates of this protein that you can see very nicely here in these microscopy images. You see these clusters of casein. And what is interesting is that actually in the cow milk, these casein are actually decorated in phosphate groups. So they have these phosphate groups there, which at a particular pH, so the pH of milk is about 6.7, so it's almost neutral, they look a little bit like that. So they have all these negative charges. And so what you have to remember is that at neutral pH, these casein globules are negatively charged, and because negative charges repel negative charges, these are stable. Now, what happens when we add an acid? For example, Coke is acidic. So when we add an acid, we have to remember the definition of pH, which is here. So pH measures the concentration of these H plus ions. So as we are adding an acid, it means we are adding H plus ions. And so as we add acid, the pH goes down, and we are adding these hydrogen plus ions, which are going to interact with the negative charges. And so as we lower the pH enough and we reach a pH of about 4.6, we're going to neutralize these charges. And now the repulsion is not there anymore, and these casing globules start to coagulate and form these clumps, these curds. And so we end up with a two-phase system, which looks something like this. So where we have a solid phase, the curds, which is coexisting with the liquid phase, in which we have, of course, water. We also have whey, which is a more soluble protein. And now whenever you have a two-phase system, small molecules can partition in the two phases depending on the chemistry, whether they like one phase better than the other. And so you may have one molecule that prefers the solid phase, so it's going to partition more there, and another molecule, the red one here, that maybe prefers the liquid phase, and so it's going to partition more there. And so this is exactly what is happening with the Coke. You saw the color compounds partition in the curd phase, and the flavor compounds stay in the liquid phase. Okay? So now, going back to the tea. So the tea, of course, is very nice, but cold in a cocktail, maybe not that much, right? Because it's very astringent and it's very hard to balance. And this is due to the tannins, which are in particular polyphenols. So these are molecules that have this kind of astringent taste. They're molecules that are actually produced by many plants, actually as a protection mechanism, not to be eaten. Well, I mean, for the vegans, you know, that's... and so the idea is that actually these polyphenols are going to bind to so-called proline-rich proteins. So there are proteins that are decorated with this proline, which is an amino acid, and this proline can act as increases the binding affinity of the polyphenols, including the tannins. Now, what is very interesting is that actually in our saliva, we have a lot of these proline-rich proteins, which of course, it's a way that protects us against these plant tannins and allows us to partially digest, effectively remove the antidigestive effects of this. Carnivores don't have these proline-rich proteins, and herbivores, of course, have a higher amount of these proline-rich proteins in their saliva, which is very interesting. Now, where are these proline-rich proteins coming from in our case? Well, the casing is one example. But you also have egg white, so you can wash with egg white, which is probably even more disgusting than with the milk, or with gelatin. And so the idea is that these polyphenols and the astringent flavors, the tannins from the tea, are going to bind the casing. They're going to stay in the curd phase. And then when we filter that out, we are left over with a tea that is much more balanced and nice. And so let's actually use this to make a wonderful Christmas cocktail.
Yes, absolutely.
Mocktail.
So I hope you all enjoyed it. Everybody enjoyed it? Very good. So now I'm going to demonstrate how it actually works to do the milk punching. So we have here our mocktail, which consists of the freshly brewed milky oolong tea with amaretto that's alcohol-free, a bit of gingerbread syrup, and the lemon is also inside as well. So essentially what we're going to do is we're going to add the drink to the milk, because what we want to do is create really controlled and slow curdling.
So if you would do the opposite, you would curdle too fast.
Exactly, correct. So what we do now is we just pour that into the milk. And if you would take a closer look, you can already see it's slowly starting to interact with one another. You can see, I don't know if you can see that.
Maybe you can place it back.
Ah, yes. Yeah,
sorry. Yeah, whoa. Yeah, it doesn't look very nice.
Yeah, so you can see it's already having an interaction with one another. So at this stage, you're basically going to leave it like this in the fridge for at least 48 hours, because the longer that you leave it, the silkier the texture becomes and the more rounder your whole drink is going to be. So let's say this has been resting now for 48 hours in the fridge. So the next step is basically having a cheesecloth to filter your entire drink. So what we want to do is we pour our milk punch on here. And the secret trick, which I will explain to you how it works, is to constantly filter over and over again. And you wait until the liquid is completely clear, and you just reuse that filter over and over again.
So how many times do you do this?
I did it at least 6 times. So it's a long process, but by the time you really get that crystal clear, which we can see already here, you can essentially just let it sit, and you can just wait for 3 days.
Well, so Christmas is the 25th, so
Yeah,
we
so
should
plan-
start on the 27th.
So you need to plan in advance. Yes.
Perfect.
Yes. So, and in the end, what you can do once you have your clarified milk punch is just to serve it on beautiful
Oh, wow.
Clear
That's
ice
here,
bowl.
it's beautiful.
homemade. And essentially what you're going to get is then a completely clear drink. And all you have to do in the end is just pour it over ice. So this is really great for when you have large groups of people for a big cocktail party. And that's
Wonderful.
it.
Oh, thank you. Cheers. Oh, delicious, really delicious. Okay, so now ready for our last technique.
Yes, so now we arrive to the last technique of the evening, which are espumas. And this is not anything new, actually. It's been existing for quite some time. And it's been popularized by Ferran Adria, famous chef. And it's the Spanish word for foam. And in culinary terms, we basically mean a light, airy, and foamy texture. But really important is that this requires a stabilizer, such as gelatin, agar-agar, or xanthan.
Yes. And so the recipe that we're going to do is what?
A deconstructed pina colada. So I thought since it was a bit depressing and raining over the last couple of days, I think it made sense to bring a bit of sunshine again into our life. So I created for you today a deconstructed pina colada, which I've already milk washed here on the side. So today we're just going to be doing basically a demonstration of how to create the espuma. So what we have here is the solution of coconut milk and pandan already mixed together. So we're just going to pour that. I'm not a chef, by the way, so if I'm doing any weird things, that's the explanation. So, yes. So now we have the coconut water and the pandan essence, which looks a bit like this. Then we add all our dry ingredients, which is the sugar, the salt, as well as the xanthan. Just gently in there. And we just shortly mix everything together. Would you like to help me stir a little bit?
Yes, sure.
Yes. So the next step is to add our...
going, eh?
Yes, just keep going. The next step is to add our stabilizing agent, which is going to be in the form of gelatin. And gelatin in its, let's say, bloomed form is kind of hard, like this. And once it's been bloomed, it's kind of like a jelly-like structure, like that. So we're going to use 4 sheets. So what we have to do is take out the gelatin and squish it out of all of its excess water, and then add it to our mixture over here.
And then slowly dissolve it, I guess.
Yes, and now we're just going to stir everything up and make sure it's dissolved. And the ideal temperature for this to function, because it requires also heat, is between 70 degrees is the appropriate temperature. Perfect. So I think it's good now.
Okay,
Perfect. So basically, once you're done with this, you can just let it sit and cool down. And afterwards, you can transfer it into a siphon and let it chill a little bit. And if you do let it cool in the fridge overnight, it can be possible that it's going to jellify and become a jelly. But don't be scared, because you can turn it back into a liquid by just letting it sit in warm water. So we want to have a quite hard texture. And now all we have to do is just build the cocktail.
Well, let's do it.
Perfect. So we're going to grab some ice.
Oh, yeah. That's the one I wanted to see.
The Collins
Wonderful.
ice. We have our pina colada. Just pour it over this beautiful ice. And the finishing touch is then to just add the espuma. So. Oops.
Wow.
You can see.
Wonderful. Oh, yeah.
Would you like to do the
Yes,
honor?
of course.
So it's quite fun. Yes.
It's really delicious. I'm gonna finish that later. Thank you very much, Sarah.
Thank you.
I need a little help here. And I think really we've learned so many interesting things, and I can't wait to actually play with these different techniques at home over Christmas and really try them out. And I hope you're going to do the same and try also to think about the science as you do this. And so with this, I want to conclude. As usual, we have our exit survey, so please do fill it out. This really helps us to improve the lectures, get ideas for new topics as well. I would like to thank all the sponsors that make this lecture happen. Follow us on Instagram. And of course, this is the last lecture of this autumn semester. We're going to have a new series in the spring with very exciting topics on chefs. And the program will be announced in January. So stay tuned and make sure you register in time. And otherwise, thank you very much for coming. And let's give a round of applause for Sarah.